everyone. Welcome back. So it's my pleasure to introduce Mr. Walton, who will speak on reflective centers of modular categories and quantum K-matrices.
Okay, so I will try to keep this a 15 minutes because I know we're hungry and lunch is right after this. So this is joint work with Robert Lalitz and Millie Yakimov, came on the archive last month. I'm going to try to keep this talk down to earth because I know this is a mixed audience. So I will define everything. If you have any questions, please ask. So the goal is to continue a study that most of us are familiar with. It's motivated. Well, one motivation is in statistical mechanics. But this will be the extent of the physics that I would talk about because I'm a mathematician. Okay, so in statistical mechanics, many of us are familiar with the quantum Yang-Baxter equation and its importance. It's used to study exact solvable models. Solutions are used to pinpoint quantum integrability. Solutions are also tied to finding solutions to the Braid equation. And many of us are familiar with the solutions as quantum R matrices or R matrices, etc. Right? Now, one mathematical way of finding solutions is to study braided monoidal categories. Especially representation categories of quantum groups or quasi-triangular Hopf algebras. Okay, so I said that the goal is to continue a study that we're familiar with. So what we're going to do is kick this up a notch. So sometimes folks are interested in let's say statistical mechanics with boundary. And in this case, one might want to study the boundary Yang-Baxter equation. Sometimes this is called the quantum reflection equation. Okay. And in this case, in order to find solutions, you need to find solutions to an additional equation. Here, the solutions are referred to as quantum K-matrices. All right, so what does this mean categorically? Here, the math way of finding solutions or quantum K-matrices is by studying so-called braided module categories. If you like Hopf algebra, if you like something concrete, perhaps you want to study, in this case, rough categories of quasi-triangular homodule algebras instead. All right, so to really bring this not down to earth, but to at least give you something to hold on to, I would say that I will argue that perhaps a favorite example of a braided monoidal category is the Driefield center of a monoidal category. It's been mentioned like in half of the talks at least. If you don't know what it is, I'll define it. So a favorite example of a braided monoidal category is the Driefield center of an arbitrary. This is an arbitrary monoidal category, right? So in the Hopf case, can everybody see it down here? So in the Hopf case, if you were to take the Driefield center of representations of a Hopf algebra, one gets that it's braided tensor equivalent to representations of the Drinfeld double of H. This is the Drinfeld double of H. Okay. So naturally, one wants to extend the spot that is orange down here. So is there a braided module analog of these constructions? So the question is, so are there braided module analogs? Meaning that if I start with an arbitrary module category M, so this is some arbitrary C module category, let's say for C braided, is there a way of building a nice canonical braided C module category? Okay, so here you start with an arbitrary monoidal category and you build one that's braided. Is there a module category analog of this? And of course, what is the Hopf analog of this as well? So what's the Hopf analog here? So we're going to answer those questions. Namely, I'm going to come up with nice module theoretic substitutions for these gadgets. Any questions on the big goal? Okay. Maybe I just switch the 2 boards. Sure, I think by your time. All right. Anything else? Okay. So again, this is a mixed audience. I'm gonna define everything. I hope you don't mind. So let's just recall that a monoidal category, I'm not going to define this. So this is a category that comes equipped with a way of putting together objects and morphisms, and it has a 1, so that the triple behaves like a monoid. It's braided. It's braided if there exists a natural isomorphism, which I'll call C, that allows you to swap across the tensor product naturally. Okay, and it needs, whenever you throw in structure, it needs to be compatible with the previous structure. So this needs to be compatible with the tensor product here. So it's compatible with the tensor product by satisfying 2 diagrams. And I'm going to draw them because we're going to draw a comparison to this later. So if I have X, Y, Z, it's isomorphic to using an associator. And then I'm allowed to keep the X alone and then switch. And then use an associator. Right, and then I'm going to keep the Y alone and then switch. All right, and then I use an associator. All right, so this is C X tensor Y Z. So I have compatibility with tensor product in the first slot. I'm also going to do this for the second diagram. You're wondering, why is she defining this? I know this. Well, I'm going to build on this later. So I need a diagram for compatibility with the tensor product in the second slot as well. So I have here Y tensor Z, tensor X. And then I use associativity. Right, and then I'm allowed to swap the first 2, leave Z alone. then use associativity. Now leave the Y alone, and I'll swap the last two. All right, and do I end up where I'm supposed to be? Yes. All right, so I'm gonna call this condition star, and this condition double star. Okie dokie. That is a graded monoidal category. Now what's our favorite example? It's a Dirichlet center. I'm going to define it. So the Dirichlet center of an arbitrary monoidal category. This is a graded monoidal category, and it has objects consisting of pairs of B and C. And this natural transformation, which I'll denote by C upper B. And here, I'm gonna put in the subscripts the natural variable. I'm allowed to swap across the tensor product. Up there, this C is called a braiding. This is called a braiding. Down here, this is called a half braiding. And again, I only have naturality in X. Okay. And it satisfies some compatibility conditions. I need compatibility with the tensor product now in X. So where, if I write C X tensor Y, V, like so, it satisfies the first diagram. Right? Morphisms respect the half braiding. What's the monoidal product? If I have two objects, well, I take the tensor product of the underlying objects, and the braiding is given by compatibility using double star. So here, if I were to write this like so, this satisfies double star. And then the braiding, I promised that this was a braided monoidal category. The braiding is given by C WB. Okay, any questions so far? All right. So again, what I want to do is I want to take all the stuff in white and upgrade it to stuff in orange. I'm not going to write in orange anymore, don't worry. So what I need to do is define what a braided module category is, and then I'll tell you what this analog is. Maybe I'll just keep it up. Not erasing.
Wet eraser on the left side.
I spent a year in Germany and I still don't know how to work this thing. Okay. And then I have to, what are you supposed to do, like talk to the audience while you're doing this? Or? No joke. Wait,
2 minutes, that was perfect.
Year. Okay, so what is a graded module category? It's still wet. Okay, so this is due to Roche, 2013. But we modified a little bit. He mostly works with right module categories. We work with left. So if I were to take a braided monoidal category, C, with a monoidal product, a 1 and a C, then a left C module category, So that's a category N that comes equipped with an action. Just like you would define a module. This is braided. It has some extra structure. Namely, if there exists a natural isomorphism, which I'm going to denote by E. I try to keep as much of this convention as possible. So we have naturality in both slots. Now here, you don't flip because you with left actions. You just have a natural isomorphism going from X acting on itself to itself. So this is for all X and C and all M and M. But you need this to be compatible with the structures you already have. So this needs to be compatible with this tensor product and this action. And that's given like so. So compatible. Compatible with the tensor product and also with this. And in order to save time, I'm not going to draw the diagrams. I will say that you have a formula that's basically first you do E and then C and then E and then C inverse. So I'm going to do this in quotes, but it's a big diagram that gives you how you would compensate for the tensor product here. And then you have another formula, which is essentially first you do C and then E and then C again. Similarly, where you compensate for the action here, right? So I'm going to call this formula star. I'm going to call this formula double star. And what's cool about this concept is, I mean, I know yesterday we were talking about like how.
Yes. May I just ask, are you assuming the module categories to be monoidal or not? I mean, you didn't write it, but I mean, I was expecting you to write so it would be monoidal, but maybe I have a different notion in mind.
But M is not monoidal.
M is not
Monoidal. No.
monoidal. Okay.
Just a category with an action.
Okay.
Yeah.
And if we were drawing the picture for the action, it would be like X wrapping around M.
Say you have a pole, you have a round. Yeah.
I see. Okay. Thank you.
But I'm bad drawing graphical calculus live, which I avoid across. But yeah, you do have a graphical calculus for this. Now, I know yesterday we were talking about rigor and how we should shoot for breakthroughs and I'm more on the artsy side. So I really like this concept because whenever you have a nice structure, you want ways of representing it. So you have a semi-simple monoidal category. You usually want the module categories to be semi-simple. Usually you want your representation to be abelian if it is abelian. So it makes sense that there should exist some concept that represents greater monoidal categories because it's so crowded. But if you're interested in applications, I just care about the art. If you're interested in applications, these gadgets have been used to study quantum symmetric pairs by Belagovic and Code. They've also been used to study extensions of braided tensor categories by Davidoff and Usage. And I was talking to David yesterday. And they're also used to study to produce categorical variants of topological surfaces. Work of this David and Bensby and Rocher. And there are many other applications. They were in the last talk. Step up for the rest of me for a little bit, so I missed that part. But very important. So we like these gadgets. Of course, we want to build more, and we're going to build one that is like this construction. Any questions? Yes.
So is there a classification of this braided modules in terms of some braided algebras? Like modules of braided.
Oh, like an O-strip type of theorem? No, but that would be cool. That would be really cool.
There sort of is, yeah.
I mean, not solid, no, yet. Like an internal harms in a way?
Yeah, that's what we did in that. There's something called the reflection equation algebra that whose modules.
So that, so
equivalent.
this is a version of Ostrich then? Or,
Yeah, you could say that, yeah,
Okay.
yeah, it's an analog of Ostrich there.
so what the quantum characters paper with.
Yes, it's, what is it called? It's called braided module categories with Bensby and Brochet.
Yes.
Yeah.
Any other questions? All right, so here's the main construction. All right, so we're gonna start off with the same setup. We have C, a braided monoidal category, and we take M, an arbitrary C module category. So we're gonna build what we're gonna call the reflective center. The reflective center, and I'm gonna denote it with an E for some reason to match this E up here. So this is of a left C module category. Doesn't have to be braided, it's just a representation of a braided monoidal category. But this gadget is going to end up being braided. So this is a braided C module category. And what are the objects? The objects are pairs M and M. And then we need a natural isomorphism defined like so. So okay, this is called a braiding. It's called a braiding. And we need something that gets close to that. We're going to call this gadget not a half braiding, but we'll call it a reflection. Okay, so we have naturality in X, so we need this to be compatible with the tensor product. So here you have X or EX tensor Y with M fixed. This is going to satisfy star. Okay, so that is the objects. Morphisms respect reflections. And now I told you it's a C module category, so there has to be an action. The action, the C action is given by, if I take an object Y and C, and I act on an arbitrary object here, it's going to be defined as, well, Y acting on the object, which we have an action. And now this reflection is given by double star. Okay, so far we have that this gadget is a C module category, but it's also braided. It's also braided. And the braiding is what you expect. It's very similar to what we have over there. It's given by the reflection. Okay. So that is the main construction. I tried to make everything look simple, but it was actually kind of difficult to make sure everything worked, especially checking these two equations were consistent. Any questions so far? Okay. All right. Now everything's erasing. All right, so the upshot is that we took C, an arbitrary monoidal category, and we can build a braided monoidal category from it using the Dreamboat center. And likewise, if we take M, an arbitrary C module category, now we can build a nice canonical braided module category from it. Now, oftentimes, nice properties of C are inherited by the Drinfeld center. Like if you want a Abelian, a finite, or semi-simple, or something like this. Same thing happens down here as well. So in this case, let's just take C to be braided tensor, because I want a Abelian and linear and all that stuff. Tensor as an EGNO. Then if this category is Abelian, when M is exact and finite, exact is sort of the general substitute for semi-simplicity in a way. You want to move outside of the semi-simple setting, you replace semi-simple with exactness here.
Chelsea, you said we didn't write abelian under,
Oh, Abelian, sorry, thank you. Thank you. All right, now if I wanted this category to be finite, I have to write the words finite. Then we need C to be finite. And we need some conditions on M. We want it to be exact and finite as well. And of course, you might want this to be semi-simple sometimes. And in this case, we want both C and M to be finite and semi-simple. So we have nice properties. Now, how exactly did we get this?
Chelsea. Does
Semi-simple.
Chelsea, sorry. Does tensor category include rigid for you?
Yeah, so tensor is an EGNO.
You definitely use it.
Because we use their results. So it gets baked in. So we rely on their fusion category paper, for instance, for this result. Yes.
If we just want the center to be modular tensor, not necessarily semi-simple, is there like a nice characterization?
This center
No.
This one?
Yes,
to be.
just like modular tensor, like somewhere between 2 and 3. It's like the non-degeneracy condition.
Oh.
Yeah.
Oh, that's what I'm working on next.
Okay.
Yeah. Grant. All right, so how exactly do we do this proposition? What's cool is that, we have that this reflective center is actually realized as something else. It's isomorphic to the center of a bimodule category. I'm not going to write down all the details, but this is due to Grinnell. So he gets just a Grinnell. You get some of these results here, but we had to make this identification first. And as a consequence of this framework, what you also end up getting is that this reflective center is not only a braided C module category, it's also a module category over the Drinfeld center. Not necessarily braided, but it is a module category. And we're going to come back to that later. All right. Any questions before we move on to the Hoff case?
I'm still confused about the main construction. What is the reflection doing? Like it's yes. How should I think about it? The way that I should think about it.
I mean, like
With a picture, for example.
Oh.
If you can.
I mean, so the graphical calculus is. Oh no, I'm doing left. Sorry, in the original papers, the categories are all right module categories. So the reflection is something like this.
Okay. Thanks.
That's it.
That helps.
You never know when you're going to answer somebody's question. Okay, so if you like Hoff algebra, now we're going to come up with a version of the Drinfeld double for this framework. So, hot case. Here, I'm gonna take K to be an algebraically closed field. We don't care about characteristic. And now if I write this tensor, I'm always gonna be tensor over K. So if I take L to be a Hawk algebra over K, we know that its categories of representations is braided if and only if L is quasi-triangular. All right, so by that, of course, we mean that there's an invertible element R in 2 copies of L, satisfying 3 equations. We have delta, the identity is R13, R23, you have 2 more as well. This is called an R matrix, quantum R matrix. And if you have an R matrix, if I write it like so, this is the 2 copies of L. How you get the braiding is you act on elements X and Y by sending this to P I acting on Y, tensor S I acting on X. All right. Yes.
The case of R that I'm most familiar with use like transcendental expressions. Is there a compelling example of such an R when K has positive characteristic?
Here and now. Wait a minute, so you want an example of an R matrix and positive characteristic?
Yeah.
Can do that now. Yeah, sorry, that's really like, it's gonna take me on a detour. All right, so any other questions? All right, so I told you at the beginning of the talk that if I take the center of this category of, let's say this is a finite dimensional Hawk algebra. I told you that this was actually equivalent or isomorphic as braided tensor categories to the category of representations of the Drinfeld center. Now, what exactly is the Drinfeld center? Well, you can think of it like, you could take H star off tensor H as K coalgebras. And you have some relations, which I'm not going to write down. And the R matrix looks like so. So first of all, you need to, since H is finite dimensional, you can fix a basis of it. In fact, let's take a dual basis. Given like so, and you can write down the R matrix in terms of the dual basis H. So this is a really, really clean formula for, oh, this might answer your question. Actually, just use a dual basis. Okay, so that's in 2 copies of the H. Now, how one actually gets this? It's a lot easier to work with Getter-Drinfeld modules. Okay, so this is a category of triples. Use this notation. Of triples, where M dot is an H module, M delta is an H co-module, and then once you have 2 structures, you want them to be compatible, you have some compatibility conditions between them. So the fact that you have that an H co-module, this gives you this copy here of this H star. And this compatibility condition gives you the relations here. Okay, and then one then gets this. So it's easier to work with the intermediate category to get this graded tensor equivalence. All right, so the goal, again, is to take this reflective center in the Hall case and come up with a version of the Drieveld's center. And so we're going to have to work with a type of intermediate category, a type of Yetter-Drieveeld category in order to get our result. Any questions on this? Okay, so now the Hoff case. All right. Let's remind people what the construction is. Don't let me erase this. It's easier if I keep it up. All right, so I need to start with C graded monoidal category. Let's fix C to be, let's say, representations of a quasi-triangular Hopf algebra. And now I'm going to start off with a nice module category. I'm not going to take an arbitrary one. Instead, what I'm going to do is I'm going to take something quite concrete. So here, B is a left L co-module algebra. So it's going to have, let's say, an action given like so. So B goes to, let's say, B minus 1, B minus or 0, with that type of Sweetman notation. This is a module category. So this is a module category. Via this action. So if I take a module over L, call it X, and I take a module in M, I'll call it M, then I get one in M by taking the tensor product of the two vector spaces, X tensor M, and now how does B act on this? I'll call this action star tilde. We have that B minus 1 acts on X. And then you have B naught acts on M. Okay. So the reason why I chose this module category is it's not arbitrary. It's actually quite nice. In fact, if L is finite dimensional, all of the exact module categories are of this form. So this is a huge class of module categories, huge class. That results due to Andrzejewicz and Mombelli, 2010. And so we're going to illustrate the main construction here, an analog of this result for this module category. So we need
Is that result you just mentioned like a
yeah. So that's in Andrzejewicz and Mombelli's paper though. Okay, so now what exactly is a quasi-triangular co-module algebra? This is due to work of Code in 2020, but again, we needed to modify it a little bit in our paper for left module categories in particular. We say that B is quasi-triangular L co-module algebra. If there's an invertible element, say K, now L tensor B, which I am going to call a K-matrix, and it satisfies 3 equations, which I'm not going to write down, but they're very similar to the equations for an R matrix. And likewise, we can use K-matrices to get gradings on B mod and use gradings on B mod to get K-matrices of B. So we get that B mod is graded now as a module category if and only if B is quasi-triangular. Right, it's the same type of result here, except we don't switch the factors. Any questions so far? Before we get to our next result?
How's a K-module algebra, I'm sorry, how's a co-module algebra related to a co-module? But is it a co-module?
Yes, it's a
Okay,
co-module and an algebra. And this has been a collection. Any other questions? Okay, now we're gonna this side.
Sorry, can I ask you a question? So in the case that L1 is, sorry. Never mind, I'll ask later.
Well, here is the main result for the Hawk case. All right, so here again, we're going to take H to be finite dimensional Hawk. H is going to be an arbitrary left H co-module algebra. And what we're going to do is we're going to build a quasi-triangular co-module algebra from A. So first, we have that as braided module categories. Oh, actually, I need quasi-triangular here, sorry. Because we want C to be braided. So as module categories over H mod, we have the following isomorphisms of braided module categories. So in this very concrete case, we can take the reflective center of the module category A mod with respect to C. And what we want to do is eventually work our way over to something that looks like a Drinfeld double, but we need an intermediate category to get there. Something that looks like yet a Drinfeld modules. Here we're going to use so-called Doi-Hoff modules. Doi-Hoff modules. So whenever you have a structure that is a combination of a module and a co-module, I guarantee you it's been studied somewhere in the literature. So it took a long time to actually find what this is. I'm going to use this notation. I'll explain it. Tons of papers on this stuff. So these are so-called Doi-Hoff modules, right? And what these are is, first of all, this is the A up here, this is the H here. This H hat we're going to use, it's a modification of H. So as vector spaces, it's equal to H, but it's sort of twisted in a way. This is related to Najib's transmuted Hawk algebras or co-Behrensized Hawk algebras. I don't really want to go into the definition, but essentially what this gadget is, it's a certain H module co-algebra. So in order to build the category of Doi-Hoff modules, we need to start off with a Hawk algebra here, a co-module algebra here, and a module co-algebra here. And then what we get is that this is the category consisting of two things, where this first pair is a module over A. The second pair is now a co-module over H hat, subject to some compatibility conditions. which I can write down very, very explicitly if you want. But we do get that this is not only a braided module category over H mod, it's isomorphic to this gadget. So this is a Yetter-Dringfeld animal, this picture up here. Now with this, we can actually build a version of the Dringfeld double. So I'm going to denote that by RHA. What this is basically it's a cross product algebra. So I need to use the H hat here with an op. And how we get this piece comes from the co-module structure. And the relations comes from the compatibility condition down here. Right, so as a vector space, it's isomorphic to a tensor product H star, essentially. All right, so we get this nice concrete realization of what the reflective center looks like. So we're going to call this the reflective algebra of A with respect to H. So that's the first part. The second part is that it's actually a quasi-triangular. Co-module algebra. All right, so we took an arbitrary co-module algebra over H, and we built a nice canonical quasi-triangular H co-module algebra. And it has a very concrete K matrix. It sort of looks like the R matrix of your Dringfeld double. So again, you need a dual basis of H. All right, and so this is going to lie in H tensor RH A. All right, so this is an H, and this is an RHA. Right. Any questions on this?
Is that? Later.
The grading for Yetter-Dringfeld modules has a very nice graphical. Do you have a similar one here? It's just the ordinary grading in action and co-action.
I didn't do pictures for this one, but it probably does, because it's very similar. I gotta say though, the compatibility conditions for doing Hawk modules, and I mean, you can write down the graphical calculus, and I imagine you can get a similar picture, but I didn't do that yet. Any other questions? All right, so to end, so first of all, oh, I erased. Oh, okay, so I said that for this category, this relative center is a C module category, braided C module category, but it's also a module category over the Dringfeld center. As a result, you actually get that this is a co-module algebra over the Dringfeld double as well. So we have explicit formulas. It took a lot of work to write that down, but we have explicit formulas. And what I want to end with is start studying a special case of this construction. No, don't erase that. Don't erase it. What did I erase? This is how I teach. Like 10% of the time is trying to figure out what to erase. I erase this. And these reflective algebras are quite nice, quite concrete. So let's take the case. So let's take the case where A is just equal to the ground field. That's a nice co-module algebra. So what you end up getting is that RHA is isomorphic to, well, A is gone, is isomorphic to this algebra. Right? And it has a K matrix given like so. Very concrete. And in fact, if we consider, so this is again, a quasi-triangular H co-module algebra. Now you can build the category of quasi-triangular H co-module algebras. So we can consider the category of quasi-triangular H co-module algebras. Okay, for which this is an object in, reflective algebras are objects in. The definition is exactly what you think it is. What's interesting is that this particular reflective algebra is an initial object. So what you get is that this particular reflective algebra is an initial object in this category. So what I mean by that is not only is it a quasi-triangular co-module algebra, you get that for all quasi-triangular co-module algebras. There exists a unique co-module algebra map going from this reflective algebra to B, with the K matrix of B being written in terms of the K matrix of this initial object. Okay. All right, any questions on this? Yes?
If I were thinking about the category of representations of H for this example, and I looked at the coend in that category, it forms a Hopf algebra object in the category. Does that coincide with this?
No, it's like the opposite end. Yeah, that's a good question. We should talk. All right, so in summary, what we have is the following. And by the way, if you want a copy of these notes, they're much neater on my paper than they are on the board. So I can send them to you if you want.
I would like to.
Yeah. Here, we're coded and everything. So, summary. So we have this continued analogy. So on one end, we have braided monoidal categories. And on the other end, we have braided module categories. Okay, so these are used to get solutions of the quantum Yang-Baxter equation. And over here, these are used to get solutions of the boundary quantum Yang-Baxter equation or the quantum reflection equation. Okay. Favorite example of a braided monoidal category is the Dringfeld center of an arbitrary monoidal category. I don't know if this is your favorite, but at least you get one example of a braided module category, this reflective center. And in the Hopf case, we have that the Dringfeld center of a category representations of a finite dimensional Hopf algebra is braided equivalent to a Yetter-Dringfeld category, and it's braided equivalent to a category of representations of the Dringfeld double. So these are all braided tensor or braided monoidal equivalences. And this is a quasi-triangular Hopf algebra. And over here, we take the Hopf case for the reflective center. Here C is a H mob, where H is a quasi-triangular Hopf algebra. We can take M to be the category of representations of a H comodule algebra. These form a large class of module algebras. We get that this is equivalent as graded module categories, the category of Hopf-Boyd modules over H. And as a result, we get an analog of the Drinfeld double, which we call the reflective algebra. A nice quasi-triangular module algebra. Okay, the end. Thank you. It talks in boots.
So Chelsea has ended even a few minutes early, so there's time for questions. Catherine?
So this picture for the it's like a double braiding, and it means something for the Hopf algebras if this is invertible. It's like the R matrix times the R21 inverse.
Yeah.
And is there like an analog of this condition, or something special that happens if this is invertible? Like not not in the category, but for the algebras then.
That's probably, but I haven't addressed it yet. That's a good question. But yeah, this is exactly like, in fact, if you take, well,
like a factorizable Hopf algebra when you have R21 R.
so this is the non-degeneracy question again. Yeah.
Yes, I guess so.
That is on the list. Good question. Thank you.
So Robert Laugard a couple of years ago defined a relative monoidal center. Is there a relation to this one?
Yeah, so I work with Robert on this stuff. It's cool. What I like about that construction is that, so for the Drinfeld center, you get reps of Drinfeld doubles, but as soon as you allow for like a bigger base than Beck, you can pick up reps of quantum groups. Yeah, so that's actually, so Robert is a co-author of this paper. That was one of our initial directions, but then it just sort of went in this direction. So the answer is no for now, but yes, hopefully soon. Yes.
One thing that's sometimes useful for the Drinfeld center is to see this endo functors of A as a bimodule category over itself. Is there a similar way to see your center constructions in terms of some class of functors?
That was also in the start notes that didn't make the book, but we,
You did mention this, that you said that you take M and you make it into a bimodule, and then you take it's at some point.
oh, Bruno's construction, yeah.
Yeah, great construction.
Yeah, it's,
Center has a description that's very close.
yeah, it's a little, I mean, it's all possible. But we didn't write that down specifically. But we did type of instruction.
So maybe you mentioned it, but if you take all the module categories of C and the constructed center, it will exhaust all the module categories of the infinity center.
Wait, what's the question?
Because it's all the module categories of C and construct the reflective center
Of each of them?
of each of them. We get module categories of the Drinfeld center, right?
Yeah, we get multiple categories, yeah.
Does it exhaust all module categories of the Drinfeld center?
That's a cool question. I don't know. That is really dreamy.
Because somehow on the Tiraviro construction, one might like Tiraviro TQFT, one might think that all the all the module categories of the bulk theory should somehow be obtained from the modules of the boundaries.
Yeah. Saucy, I don't know the answer to that.
If it appears there are no other questions, let's thank Chelsea again.